All right, guys. Welcome to the session, guys. We're going to talk about EVPN VXLAN, specifically with a focus on the building blocks, or what I will call out as building blocks in EVPN VXLAN for multi-service fabrics. My name is Aldrin Isaac, and I'm with Juniper Networks. I'm also one of the co-authors of EVPN RFC 7432. I've been involved with EVPN before it was EVPN. So just to get started, I ripped this one from Google slide somewhere. Network system as a whole is basically composed of multiple subsystems. One of the subsystems is the network virtualization subsystem. And that is, in the case of Google, it's Andromeda. In the case of what we're going to talk about today, it's going to be EVPN, right? More specifically, we're talking about EVPN in the fabric. So this is as opposed to EVPN implemented on compute nodes or with smart NICs. Specifically here, it's going to be EVPN in the physical fabric. And this is what I refer to as the multi-service fabric. All right, quick agenda. I'm going to do a quick recap of EVPN fundamentals. First 5 slides. I'm not familiar with what the audience knows or doesn't know, so in order to bring anybody up to speed who needs to be brought up to speed, I'm just going to do a quick recap. Forgive me if you already know this stuff. And then we're going to talk about overlay options or overlay building blocks, if you will, for east-west traffic. And then we will move on to some interesting use cases I want to cover that just sort of highlight some of these building blocks that we will talk about in lesson number 2. And then lesson number 4, we will talk about north-south traffic flows in using EVPN-based service chains, using the building blocks that we cover in lesson 2. And then finally, if we have time, we'll talk about some interesting efficient overlay replication options in EVPN. Okay. Some things to note about this tutorial. It's all 100% EVPN. There's no mixing with any proprietary technology. Everything here is EVPN, all EVPN. Second thing is that this is about stuff that's been implemented, is in the process of being implemented, or is capable of being implemented with EVPN. So because I talk about it, I'm talking about it in a very vendor-neutral way as a co-author of the RFC. This doesn't mean that everything you see here is actually implemented. I'm talking about it as a representative of EVPN, not as one of a vendor. So I will not go into route and tunnel header details, although some of this may be straightforward for most of you guys, and for some it might be a little bit too much detail. The model that I'm going to be using here, for those of you know, is VLAN aware model. The VLAN base model with EVPN is, you could consider a subset of the VLAN aware model. It's a VLAN aware model with one VLAN and a few procedural differences, very minor procedural differences. And then as we move forward, I think even from the beginning, we'll probably be moving at a really fast clip. So hopefully I'll keep you guys engaged. All right, so to begin, we need to actually have a reference model. So I'm going to establish one. Basically, for this tutorial, we have this concept of a tenant. Tenant is basically Pepsi, Coke, payroll, engineering. These tenants are composed of groups of location-independent endpoints. Groups are manifest as subnets for this tutorial. These subnets are routed to other subnets using a distributed routing function. And all intra-tenant traffic we will refer to as east-west traffic. So inter-subnet traffic within a tenant and intra-subnet traffic within a tenant is east-west. So tenants can be routed to other tenants and to external destinations through service function chains. So that's where we'll talk about service function chains. And this is what I refer to as north-south. So any extra tenant traffic to me is north-south. Okay, at least for this tutorial, that's what we will refer to as north-south. So tenants and groups are implemented, obviously, as overlay virtual networks. I will occasionally refer to these things as different things. One thing you might hear me say is L3 virtual networks and L2 virtual networks, or L3 VNs and L2 VNs. Means, basically IP and Ethernet overlay networks. Now, the network virtualization edge, or NVE function, which is referred to as in NVO3, Network Virtualization over 3 Working Group, can be implemented on the TOR or in a compute node or SmartNICs. And we're going to be emphasizing implementation in the physical network. These NVEs are also referred to as provider edge in SP networks, and VTEPs and VXLAN networks, which PE stands for, I think I said this already, provider edge, and VTEP stand for VXLAN tunnel endpoints. If I use the word NVE, PE, VTEP, all means the same thing. Okay. So I just want to draw some parallels between the classical network and EVPN. We start first with our VTEPs that are connected to an IP fabric. In the classical network, you have physical switches. In EVPN network system, you have a virtual switch. In RFC 7432 lingo, it's called a MAC VRF. If I say MAC VRF, I mean virtual switch. If I say virtual switch, I mean MAC VRF. Okay, so hang on a second. Sorry. In the physical switch, we have VLANs, VLAN tables specifically. In the EVPN network system, within a virtual switch, you have VLAN tables as well. Same thing. In the classical network, you have VLAN trunks connecting the physical switches with VLAN channels connecting the VLAN tables between across the physical switches, creating an adjacency between those tables. In the EVPN network, you have VXLAN tunnels connecting the virtual switches, and you can, with these tags called VNIs, virtual network IDs, that kind of are the corollary between the classical networks VLAN trunks, right? So you can think of the VXLAN tunnels as sort of what the same as the VLAN trunks that connect the VLAN tables together. Okay, actually, let me go back 1 second. The learning in the physical switch between the VLAN tables happens in the data plane, and through flood and learn in EVPN, it's done in the control plane. Routes are exchanged, routing information exchanged between tables using BGP, and along with those routes are the information necessary for the tunneling encapsulation, like VNIs. And then in the classical network, you have physical routers with connected by physical ports with OSPF or BGP to use for route exchange. And in the EVPN network, you have virtual routers that are exchanging routing information with each other using the MP-BGP control plane over BGP, right? And then finally, you have a connection between the routed network and the bridge network on the right with a physical interface on the left using integrated routing and bridging interface. And you can see there's a lot of correlation between your classical network and your EVPN network, to some degree almost one-on-one, minus the fact that there's control plane learning on one side and data plane learning. And additionally, the classical network is considered single tenant, and EVPN network system is multi-tenant. Okay, for those of you who aren't familiar with BGP-based VPNs, just a quick overview. We have our VTEP. It has a BGP component, specifically a multi-protocol BGP component that implements EVPN. And then you have the same thing on other VTEPs, and they exchange routing information with each other, either through direct peering or preferably through a route reflector, which simplifies the configuration. And then we add to that the We add to that the tables that we just spoke of in our previous slide, the VRFs and the MAC VRFs and the corresponding L2 tables within those MAC VRFs. We assign these tables IDs, data plane IDs, say 100 and 200 in this case for VXLAN VNIs and Ethernet tag. And typically in the VXLAN network, you just assign the VNI, VXLAN VNI, and the tag is set to the same value. And there's also a VXLAN tag associated to the VRF as well. And now you export the routing information that's local using MPBGP to other VTEPs. And the way you do this is by associating what's called a route target, like a topic ID, on your routes, and importing routes from other VTEPs with route target IDs that you are interested in. And typically, in the general case, what you export and what you import are the same value, right? And that gives you what we refer to as full mesh VPNs, right? In the process of exporting and importing routes, you populate your routing tables, your forwarding tables, your L3 VPN IP routes in your VRFs, L2 routes in your MAC VRF, and the information that you need with those routes corresponding to the tunnel information you need that correspond to those routes to establish the tunnels, and then the L1 routes, which we'll talk about really quickly in the next slide. And this gives you your overlay VPNs. Okay. So we talk about route types first by layer. So EVPN has some route types for L2. Type 2 MAC IP routes are unicast specifically. There's MAC only and MAC plus IP routes. Type 3 is for the BUM, and it's called the inclusive multicast Ethernet tag route. So if I say inclusive, I mean everybody gets it. And then type 6 is for selective, so only the folks that are interested. We'll cover type 6 a little bit more in detail towards the end. Then we have the L3 routes, IP routes, namely the type 5 routes. There's two forms of it. We're going to cover the VRF to VRF form. There's actually a MAC VRF to MAC VRF form, which is the original form. The VRF to VRF form was introduced later. And for this tutorial, we're just going to cover the VRF to VRF form of type 5 routes. And yeah, you can barely see the highlights, but these routes that I highlighted are kind of like layer 2.5, if you will. The MAC plus IP route is used for ARP proxy, and you know the ARP is sort of a layer 2.5 function. And then, you know, type 6 is, you can think of type 6 as IGP snooping, supporting IGP snooping, which is kind of a 2.5 function as well. And then the MAC VRF to MAC VRF is sort of a 2.5 as well. We're not going to cover that one. Now, the last category of routes is the L1 routes. This is unique to EVPN. It actually trades routes related that are basically about the interfaces. And yeah, there is some additional detail which I'm not going to cover here, but as you can see, there in EVPN there is L1 all the way to L3, right? And that's one of the interesting things about EVPN versus others. There is a very nice integration between these layers in EVPN, right? And that's sort of what makes it as robust as it is. It actually takes into account the relationship between layers. Now, same route types looked at a different way. So there's 4 route types for unicast and 6 route types for replication, right? One thing that I want you to note is, you know, if you don't need multi-homing, you don't need the multi-homing routes, right? If you don't need, you know, replication, you don't need the replication routes. So there is an aspect of EVPN that you may not see in implementations where it is, one of the goals of EVPN was to be policy-based. So you can actually craft quite some interesting scenarios with EVPN by what you trade and what you don't trade with other VTEPs, right? And we'll cover some of those concepts today, right? So yeah, These routes are basically, and the procedures around these routes are, they basically form the primitives of the building blocks that we're going to cover next in our tutorial. And so with that, we're done with the basics. We're going to talk about different 4 overlay service models, which will be basically form the building blocks for our subsequent discussions, lessons as well. The first one is pure bridging. It's very basic. We're only using here the the layer 2 route types that we spoke of in our earlier slide. And for this one, we're using the type 2 MAC only route, and the type 3 route for inclusive multicast replication, which is basically for broadcast. And then obviously the VXLAN, as we spoke. This is just the basic building blocks. So we're gonna build on this in the next 2 overlays models. If you want to do routing, well, you're going to have to do it with an external gateway, right? But interestingly, and we're going to talk about this in the next 2 slides, after the next slide actually, you can do ARP suppression with L2 only overlays. And for that, you add the MAC plus IP route. Okay, a little bit of detail here. Yeah, we have here leaf 1 and leaf 2. We're going to add the MAC VRF for tenant T, add the VLANs, VLAN 1 and VLAN 2 for tenant T. We're going to set up a L2 VPN or policy to exchange routes between these MAC VRFs. So that policy is going to cover both VLANs, VLAN 1 and VLAN 2. So basically, this is what we call an EVI. So if I use the word EVI in the context of a tenant, it's not just one VLAN, it's basically all the VLANs of a tenant, right? And all the VLANs of a tenant can be described in one policy that is implemented at the MAC VRF level, right? So yeah, just note when I use the word EVI, it covers all the VLANs that are participating in a tenant and configured within the MAC VRFs. Now, the 2 route types, as I said, were type 2 and type 3. Now we have the routing information that's been exchanged between those MAC VRFs and used to populate the VLAN tables, along with the VNIs of those VLAN tables, so we can transport packets between tables using VXLAN. Okay. So before I get into the next 2 service types, which are integrated routing and bridging overlay service types, we'll talk about our proxy because they're an important component of the next 2 types. So our proxy is used for 2 functions, namely our ARP table synchronization and our ARP suppression. Before I describe what ARP table synchronization is, let me describe how ARP tables are populated in traditional routed networks. If you have a subnet and there's, say, 2 gateways in the subnet, the way the table is populated is when an external packet is being forwarded into a subnet by a gateway. If it doesn't have an ARP entry, if it doesn't have a MAC for that particular IP, it sends out an ARP request, it gets an ARP response, and it populates the ARP table. The second gateway that we just described, it has no idea the first gateway and create an ARP table entry. And so its ARP table, it doesn't have an ARP table entry for that same host until a packet arrives on the second gateway to be forwarded to that same host, and then it sends out an ARP request and it populates the ARP table. In EVPN, it's very different. These ARP tables are actually sort of pre-populated, and the way they're populated all at the same time. The way they're populated is that the leaf VTEPs at the bottom are snooping ARP, and they basically extract the IP MAC bindings from the sender field of ARP requests and ARP responses, and they send it in the control plane as MAC plus IP routes. All the VTEPs participating in a subnet, store that MAC IP binding in a MAC IP binding table. Any integrated gateways like the ones at the top, take those bindings and install them in their ARP tables. And if you have two gateways, integrated gateways, they're both getting their ARP tables updated at the same time. If you have four, all four, 8, all 8, and so on. So they're all getting synchronized at the same time. Yeah. Now, ARP suppression uses basically the same machinery, so that MAC plus IP information advertised in the MAC plus IP route is also, like I said, stored in the MAC plus IP binding table for that for a particular broadcast domain. And so if a remote a VTEP that receives a ARP request locally from a local end system will respond to the will intercept the ARP request, right, and respond to the requester locally by generating an ARP response locally, and by doing so, it doesn't broadcast it the ARP request across that the broadcast domain across the subnet. Yeah. So now, if it doesn't have the IP MAC binding entry, it will just re-inject the packet and let it flood. Okay. And when the response comes back, if a response comes back, the VTEP that's closest to the responder will take the ARP response, extract the MAC plus IP binding from its sender field, and advertise in the control plane, and that will be the last time that that thing will get broadcast again, right? Yeah, there used to be a working group in IETF called ARMD, Address Resolution in Mega Data Centers, because it was such a huge problem in mega data centers, and EVPN just basically addresses this issue for everybody with ARP suppression capability. I'm going to skip this one. So there is an additional feature, I guess you can add to it, which is the support for gratuitous ARP. What I spoke of before, the leaf VTEP, extracts the MAC IP binding from an ARP request response, sends in the control plane. The remote VTEPs, they just install it in their table. They don't reflood it or anything. They just install it in their table and wait for an ARP request to come in, and they respond, right? Well, and when it comes to gratuitous ARP, if you do that and you don't flood it, what happens is, the systems, there's a legitimate reason why it needs to be flooded, and all the VTEPs are holding on to the MAC IP bindings and they're not reflooding it, right? So with gratuitous ARP, whenever there's a binding change, a new binding or a binding change, the remote VTEPs will actually just reflood it from the control plane back into to local end systems participating in the subnet, the systems, the modern operating systems basically ignore ARP, gratuitous ARPs that they do not have an existing binding for. If they had not asked for that ARP entry, they'll just quietly ignore it, right? It doesn't, in the old days, you could build up ARP tables, massive ARP tables, and have problems for yourself, but the newer systems would just ignore it if it hadn't requested for an ARP entry earlier, right? So this is actually not a problem in modern operating systems. And we'll use this in our examples section for something interesting. VIP mobility, mobility in bridged mode, Wi-Fi's, VM mobility, all of these use gratuitous ARP quite liberally. Okay, so with that, we're going to start our second overlay type, which is centrally routed bridging. In centrally routed bridging, as its name implies, the routing happens at some central point. Whichever point is implementing the central routing, the MAC and IP addresses for each subnet should be the same. I'm going to refer to the central routing point as the CRB gateway, just because the rest of it, it's kind of a mouthful. So just if I say CRB, I mean centrally routed bridging. So CRB gateways can be placed anywhere. It could be on a server, it could be, in a spine, it could be wherever, right? There's no placement rules, as long as it's within the domain of the VXLAN tunnel. CRB access, which is implemented on the leaves that end systems connect to, are just performing bridging exactly the way the pure bridging that we spoke of, nothing different, exactly the same thing. So the only thing we added on top of the pure bridging was someplace in the network which is providing routing. Right? That CRB gateway will advertise its MAC plus IP, MAC and MAC plus IP as type 2 MAC only and MAC plus IP routes. And so all of these VTEPs will know, okay, this MAC IP is over there, and it can forward MAC on MAC to the gateway for packets that need to go to the gateway, and it forwards directly to other VTEPs for other MACs, and also has a MAC plus IP for ARP synchronization of the gateways, as well as ARP suppression we just spoke of. So some of you are probably familiar with distributed inter-subnet routing and bridging. I will refer to that as edge-routed bridging, because it's a lot less of a mouthful. You may ask, well, why do we need CRB? Why not ERB? There are use cases for it. For example, the CRB gateway might be implemented on a firewall, right? And you can't do what the firewall does on leaf switches, right? It may be that the CRB gateway has better ACL scale, or it implements some other type of function that's useful. A little detail, we start with the pure bridging, exactly the same. We can do intra-subnet with pure bridging. We add a gateway, we add the MAC VRF for the tenant. We join the tenant's EVI. We add a VRF at the gateway and connect the VRF to the subnets with integrated routing and bridging. And now we have inter-subnet routing at the gateway. And that's basically it. The third overlay model is edge-routed bridging. In edge-routed bridging, we move the routing function from central point all the way to all the leaf VTEPs where the tenant's end systems are connected. So our tenant VRFs are pretty much everywhere where tenant end systems are connected. And all these gateways for every subnet needs to have the same MAC and IP for this to work. There's two forms of edge-routed bridging. There's the asymmetric form, exactly same route types as CRB. It requires the MAC plus IP route for ARP synchronization for inter-subnet forwarding. The drawbacks of this approach is that you need the VLAN of the tenant everywhere where the tenant's VRF is configured. So that's a big drawback. So I will talk about type 5 based symmetric ERB. This is a form of symmetric ERB. So a form that we implement. There's some room, I guess FUD out there that Juniper doesn't implement symmetric. We implement type 5 symmetric. And this is different from the type 2 symmetric. So type 5 symmetric uses type 5 routes to do symmetric inter-subnet routing. Basically, how this works is that locally learned ARP entries the IP from the locally learned ARP entries are imported into the RIB and advertised as host routes as type 5 host routes. And they're imported by all of the VRFs of a tenant. Advantages is that, by the way, the type 2 MAC plus IP route is still used, but it's used for ARP suppression. Now, the advantage of the symmetric approach is that you don't need to configure the VLAN of the tenant everywhere where the VRF of the tenant is configured. And that means it's much more scalable. So a little quick detail. We start with, again, with the pure bridging service model. And then we add the VRFs to all the leaves, for the tenant VRF to all the leaves. Now we have local inter-subnet routing. With the type 2 MAC plus IP route, ARP table synchronization, we have inter-subnet routing between leaves, and this is asymmetric. Okay, so you can see the path is L2, L3, L2 on leaf 1, and then across L2. And reverse will be, again, L2, L3, L2. L2, L3, L2, L2. Okay, so it's the bidirectional forwarding pattern is asymmetric. For symmetric, we exchange our host routes, learned from ARP, locally learned from ARP as type 5 host routes, and now we do symmetric, right? So now it becomes L2, L3, L3, L2, and the same in the reverse direction, and in that forwarding pattern is what we call as symmetric. Okay. All right, and the final overlay service type is the IP routed model. The IP routed model is just basically, for those of you who know MPLS IP VPNs, it's the same thing, but it's using EVPN type 5 and VXLAN. So the IP overlays are useful for north-south traffic flows, for service chaining, and as well as for tenants that don't have no need for Ethernet bridging. Yeah, we spoke of that type 5 prefix route. Now, if you need mobility here, you need to do BGP all the way to the host, right? And if you have a workload that needs to move from one host to the other, the original host has to withdraw, and the target host has to announce. And it's also useful for these overlays are useful even for folks who don't believe they need it. For example, if you're running an IP-only infrastructure, you can still use routed overlays to run lean core. So you don't have any workload state, workload IP in your spines, etc. You can use it for lightweight multi-tenancy, like you have a dev environment and prod environment, and you want to keep them air-gapped, but over the same infrastructure. And then you can use, the tunnels themselves, the tunnel headers themselves, like particularly NVO3 headers, like tunnel encapsulation data plane protocols like VXLAN GPE and Geneve also bring in additional option headers that you can use, for example, for a group-based policy, as well as in situ OAM. So there are some advantages of having other advantages besides overlays of having the tunneling headers. So you can have different overlay topologies with the IP-based overlays. In this case, we have a full mesh topology, and the way the full mesh topology happens here is we import and export the same route target, and we have basically a full mesh topology, right? All of these VRFs see each other's routes. There's a hub and spoke, or I would probably also be referring to this as directional VPNs, where in this case it's the border gateway, VRF, VRFG announces its routes with RTG and imports routes with RTX, and the VRFXs do the exact opposite, right? And this is directional. Now, you might say, hey, if VRFG advertises down a default route, you can actually, forward from VRFX to VRFX on leaf 1 to leaf 2. That is possible. So if you don't want that behavior, you can implement a routing table policy to prevent that behavior, or there are other ways of doing that as well. Right. This type of VPN you don't want to do with MAC-VRF to MAC-VRF. You don't want to do this at the L2 level. It gets tricky fast. Right. So this sort of very flexible topology is probably better reserved for L3 VPNs. And we're gonna be using this this particular hub and spoke or directional VPNs in our service chaining discussion. Okay, so here's a case where we're going to basically we have a need to connect this edge routed bridging tenant to the external world. We add our border gateway with VRFG, add a hub and spoke VPN between VRFG and the tenant VRFs, and advertise down the default from the tenant and the VRFG and advertise up the host routes. And we have, and also announce to external, maybe an aggregate of these host routes from the VRFG, and we have communication between the tenant end systems and whichever external networks you need to reach. Okay. All right. So I'm going to skip over this in the interest of time. Now, everything we spoke of up to now is no multi-homing. So we're going to talk about multi-homing now. You didn't need multi-homing if you didn't need multi-homing for any of the overlays, but if you do need multi-homing, you need to add this building block. Basically, so here's where we're introducing the L1 route types, right? EVPN supports N-way multi-homing, where N can be greater than 2. MC lag is two-way multi-homing. EVPN supports more than that, technically any number. But and we'll cover an interesting example for how we can use this N-way multi-homing in a few slides. There's no ICL link required, as with MC lag. We use here type 1 and type 4 routes. And when you introduce selective multicast, which we'll talk about a little later in our tutorial, you have to add the type 6 and 7 routes as well. So multi-homed end systems are identified in the overlay by a unique segment ID, otherwise referred to as a ESI, Ethernet segment ID. The ESI basically represents a split horizon boundary, right? It doesn't really identify, it does identify an attachment point, but effectively what it is, its purpose is to identify split horizon boundary between two, L2 entities, right? It could be a host, it could be another network, but it defines a unique split horizon boundary between those two, and what crosses the boundary is not allowed to cross back, right? That's basically what an ESI is. So only one member link of an ESI is allowed to forward replicated packets, and that member link is known as the designated forwarder. It can be at the DF can be at the granularity of a VLAN ID, but for this tutorial we'll leave it at the granularity of a port. And then interestingly, RFC 7432 does suggest ways to make this ESI discovery automatic, ESI discovery and generation automatic by snooping LACP system ID and generating ESIs against the system ID in LACP. But also, interestingly, the type 2 auto ESI snoops on the BPD root bridge, right? So an interesting outcome of the second one is if EVPN is multi-homed into a spanning tree network, and that network partitions, and each partition gets a new root bridge ID, EVPN will actually heal it, right? And an interesting thing you can do about this is divide and conquer, build. If you have a giant L2 network and you want to kind of break it up eventually over time into EVPN, you can use this as a way to do it. Okay. IP multi-homing is here. I think most of you know what it is. The Ethernet multi-homing was related to the first 3 overlay building blocks, the pure bridging, and the 2 integrated routing and bridging overlays, CRB and ERB. IP multi-homing is how you multi-home in the pure routed overlay type. There's 2 forms of it, and we'll skip the details, right? It's just here for completeness. Okay, and that was lesson 2, and this is lesson 3. Just going over some special use cases using the building blocks that we spoke of. So here's an example, underlay routed overlay subnets. It's a mouthful. Basically, the subnets themselves are overlay, but the routing happens in the underlay. Okay, and this is where you might have a single tenant from an L3 standpoint. It's a single tenant variant of edge routed bridging, where the routing again happens in the underlay. If you're familiar with Junos, it's INET 0. As its name implies, there's no virtualization nor tunneling for IP. The very, very basic use case is I like MC-lag, but I want an open version of it. I have two switches, and my subnets only span these two switches, and I want to multi-home across these two switches, right? I want to do it with EVPN, right? And you can use, but I want to route in the underlay. So you can basically use EVPN simply as an MC-lag replacement, an open variant of MC-lag. I don't want to burn any ICL links or whatever. The expanded use case is I just want to do my overlay subnets. I want to place my overlay and my endpoints and my subnets anywhere in the network, and but I still want to route in the underlay. All right, and you can do that, and you can throw in ARP suppression. Comes for free. Okay, example 2. Now we have legacy access switches, and we want to kind of bring that into EVPN. In this example, I have these access switches. They don't support EVPN, but they support lag or MC-lag. And this is sort of a variant of edge routed bridging. I have a set of EVPN leaves, right? I'll call the set as the collapse spine. The man who coined the word is right there, Damien. Basically, if the subnet does not span beyond this collapse spine, I can just advertise the subnet routes. I don't have to advertise the host routes. So it's a variant of ERB where I'm advertising subnet routes instead of host routes. And I'm doing EVPN multi-homing down to the access switches and MC-lag up from the access switches. And this is an example of N-way multi-homing, right, using N-way multi-homing in EVPN. The collapse spine pods can be part of a larger IP fabric. We've seen this as a transitional step that some companies use. It's really hard to change out your access switches because of all the connections and the disruption that happens at that layer, but you want to introduce EVPN starting at some layer, maybe the next layer up, and maybe you want more than 2 members of your collapse spine. Reason being, well, if you're doing maintenance on one, you're standing on one leg. Well, if you have 3, you do maintenance on one, or one goes down, you still have 2 left running. So that's an interesting value prop for the N-way multi-homing. Okay, the third example is a bum-free subnet, and this is where the gratuitous ARP proxy function comes in. So some operators, they need the L2, but they just want unicast. But unfortunately, L2 comes with broadcast, right? And there is something you can do about that. So basically, the broadcast, what is it needed for? It's just needed for ARP, right? And just because you have ARP, you now need to have broadcast. So with EVPN, you can basically enable ARP suppression with the GARP support that we spoke of before. And then, like I said, you can use the policy knobs, right, to suppress the sending and receiving of type 3, 6, 7, and 8 routes, which are the ones for any multi-destination frames. And now you have an L2 network that is just for unicast, right? And the nice thing about it is there's no bums, so there's no loops. There's no flood list state scale issues, right? Because when you have bum or you have any type of replication, you have flood lists, and that consumes state on your chip. So you have none of that. And it's IPVPN-like, but it has the Ethernet plug-and-play properties. The caveat is that the systems that are participating in such a network have to send GARP, right, when they start up. and when they move. Okay, so that's a requirement. It's actually possible to do that on Linux. I don't know how you do it on other systems, but typically, if this was an AP, a bridge mode AP, when an end system moves, the AP will do a gratuitous ARP on its behalf. If it's a hypervisor, the hypervisor will do a gratuitous ARP on behalf of the workloads that move, and including at the time when it comes up. So there's a number of cases where it's just fine. So if you have a bare metal system, you just have to make sure that this is in place. Okay, I am going to skip this one because I think it takes like 15 minutes to explain. But that was a kind of I was just throwing it out there as a way to do PVLAN, right? You can do PVLAN, but the best way to do PVLAN, by the way, is probably group-based policy. So if you're interested in PVLAN, go look up group-based policy. The final example I have here is VXLAN, MPLS, VXLAN, SRv6 coexistence. I've seen some telco cloud folks who basically need MPLS or SRv6 to communicate across their WAN fabric, and so they believe that east-west traffic must also use the same end caps, right? If I'm using SRv6 across my fabric, or I'm using segment routing across my fabric, my east-west must also, my intra-fabric must also use the same end cap, and that's not true, right? I can still use VXLAN end cap and all of the stuff we just spoke of in lesson 2, and I can coexist with an MPLS, in this example, an MPLS VRF participating in an IP MPLS VPN, also implemented here on the leaf. My front end over here, I have back ends, and front ends of front ends are the ones that need to communicate across the WAN. It could be a VNF or whatever it is. It can have a second interface, and the second interface, it could be a logical interface connected through a VLAN trunk to where a particular VLAN goes into an MPLS VRF, and you can route it that way. So that's one form of coexistence, and it doesn't seem so pretty. But another way is I can get rid of that interface, and I just basically leak routes between the MPLS VRF and the VXLAN VRFs, right? And it's kind of service chaining, right? So all my east-west traffic in this case is actually VXLAN, exactly like as we did in lesson 2. And my north-south is now going over MPLS VPN. Okay. Do the same thing with SRv6, right? I don't want, there's not a lot of tours that implement SRv6, but the reality is that SRv6, it really, I don't think that you need SRv6 at the Tor, right? Usually with SRv6, you have a workload, and it needs to you're trying to do egress peer engineering, workload asks the controller, hey, tell me which way to go. Controller gives it a segment list, right? And the first segment, the first hop in that segment list is actually not the Tor. It's maybe the data center gateway, right? So the Tor actually just forwards on IPv6, right? And same way back. So here you have the workload knows SRv6. The next, next hop in the segment list knows SRv6, but the Tor doesn't have to know SRv6. It just needs to know IPv6. And I'm just leaking routes here, right? So there you go. That's the end of lesson 3. Now we're going to talk about this is a concept discussion here. I'm not talking, technology. This is mostly abstractions, so just kind of bear with me on these abstractions. It's just stuff to think about. So in my book, the service chains are basically, for this tutorial, the reference model for service chains is anything that needs to go between tenants or any extra tenant communication is going through a service chain, right? Either an conceptual service chain or actually a service chain with real service functions in it, right? Okay, I'm going to skip this one because I skipped this piece in the last lesson. So here, we've actually seen service chaining already in this lesson. I'm sorry, in this tutorial. was that example where we had the ERB that needed to go out through the border gateway. So let's just say that border gateway was a service, implementing an MPLS VPN gateway. It's a service function, right? And we connected that service function to the tenant VRFs using a directional VPN, right? And we just implemented service chaining. Same here. We connected a MPLS VRF, which is effectively an MPLS VPN gateway, right? A service function, you can look at it that way. And we connected them, you know, into a service chain. And this is much more of a distributed form of it. Okay, so service chaining is basically kind of looks something like this, right? Lots of stuff in between, you know, end systems. But basically in the EVPN world, we're using exactly the same building blocks. One of those 4 types, right, are involved over here. So, you know, in this case, I'm using ERB over here, ERB on the left and the right side of these service function. This here is my service function block. Over here, I'm using a pure IP, left and right. This is my service function block, right? And I'm connecting this with the directional VPNs over here, right? And we'll talk about the external gateway in a second. So service chains are, for this tutorial, are bidirectional, right? They go left and right. If you try to, you know, stick a multi-directional service function in the middle of a service chain, you don't get a chain anymore. You get mass confusion. So just for the purpose of this lesson, we're going to kind of play service chain Lego. I have a little bit of symbology here, just to make it easy. Otherwise, the pictures get really hairy very quickly. So I have some service function types as examples. Service function to connect you know, tenants together, to connect a service function to the underlay, a service function block for L1, right, and another one, service function block for L3 service functions. I'm going to skip this one because I don't have time to talk about it. And then I have integrated IPsec gateway and integrated IPVPN gateway, and a service function that connects me out to the external world, right, and external gateway. So just dipping in a little into the and 2 of those service function blocks, one that supports the L1. Basically, what we're looking at is exactly using the stuff we spoke about, right? We have here a IP overlay building block on the left and on the right. We're using a directional VPN on the left and the right to connect to a building block, whether it's an ERB, CRB, or other tenant, or another service function block on the left. Same thing on the right. And with service chaining, you're moving the routes on the left. What is it to you? Can't tell my left and right. Yeah, you're moving your routes from your left towards the right, and your routes from the right towards the left through this chain, so you can have the bidirectional routing. How you do it, we're not going to get into the details of that. You can use BGP, you can use static routes, whatever, right? But you're basically communicating them across these directional VPNs between VRFs. This is an IP connected service chain. You can do L2 connected service chain, but I don't have time for that today. So that was a case where both sides of the service function are part of the service function block. In this case, only one side, it's one-legged, because the other leg of the service function goes outside, right? The same, okay, in the case of L1, bump in the wire, these 2 VRFs are adjacent. And in the case of L3, they're not adjacent, they're adjacent to the left and right interfaces of the service function. But again, the routes on the left have to be propagated to the right, and the routes on the right have to be propagated to the left. Okay. Now, the important takeaway here is we used exactly the same 4 building blocks in service chaining. Okay, for service chain scaling, we have our 1 block here. You can add as many as you like, right? As long as it's using the same template, right? Connected to the same directional VPNs on the left and the right. You've just scaled each service function. Now, there's some cases where you have an active standby service function, and those active standby need L2 adjacency. And they're maybe using virtual IPs. For that, you can just use an ERB as your mechanism, right? Instead of IP. Right. So the left and right is still done through the VRF using, still done through the VRF using directional VPNs, but the L2 is supported for these guys to have an adjacency, L2 adjacency with one another. I'm going to skip this one. Okay, so here's an example of where you have a tenant with multiple chains, where each tenant may have more than one chain associated to it. So all the tenants on the left need to talk to the tenants on the right. They go to the top service chain 1. For the tenants on the left to talk to each other, they go through service chain 2. For tenants on the right to talk to each other, they go through service chain 3. Right, so an example of where you can do, multiple chains, right? Again, all using the same building blocks. This is an example where chains are connected to other chains, right? The top 2 tenants need to go through a load balancer. The bottom tenant needs to go through a firewall, but they both need to go out to their campuses, for example, using an IPsec gateway. And that's an example of branching chains or these connected chains. And you can also have scenarios where one chain depends on another chain. In this case, this chain ends in an IPVPN, which has a transport tunnel that depends on the underlay fabric routing. But the underlay fabric routing must exit the network using a service chain, right? So you tie the underlay fabric to a service chain, and maybe it needs an encryption. So this guy goes out, under, encrypts, and out. Okay, so that's dependent service chains, right? And these are all just concepts, right? You may be able to do a lot more, right? But if you simplify things into these abstractions, I guess the point is you can find a lot of different things you can do with it, right? And we just use 4 building blocks here, right? Okay. Gateways, these N-way forwarders are kind of unique animals. Yeah, I don't consider them as something you would stick in the middle of the chain. You would just have mass confusion. But you can, stick them at the ends of, you can stick them at the ends of your chain, right? Typically, your external gateways will be connected directly into your tenants, right? They don't have a directional VPN as the connector. They just connect directly, and then they can connect upstream into a chain. I'll skip that one. Multicast through chains is interesting. If you have a need for talking about multicast through chains, talk to me. We're not there yet. You have to use L2 linked chains for getting multicast through. I don't have time for that. Okay, so finally, how much time do I have left? 2:30. Okay, I got time. Finally, we have overlay replication. This is my last section here, last lesson. So overlay replication uses over-the-top signaling. So means we're not doing signaling hop by hop in the underlay, which means we don't have any traditional underlay multicast protocols, and that's a nice thing, right? Which means that you don't have tenant state in your underlay, which is a nice thing, which means you're running lean core. Okay, so you want overlay replication. The problem with overlay replication is, you also, technically, depending on your implementation, your convergence is effectively the same as your unicast convergence. The problem with overlay replication is not so efficient, especially when you're talking about ingress replication. But EVPN does have some, new capabilities associated to it that improve overlay replication. We'll talk about that in this last section. The first thing we'll talk about is selective multicast replication. With selective multicast replication, unlike inclusive replication, if all the VTEPs that are participating in a subnet, whether it's broadcast, unknown unicast, or multicast, they all get the frame, right? And in selective multicast replication, we have this additional type 6 route where we can signal the VTEPs that have interested receivers for an IP multicast. Right. So if I have 100 VTEPs and I have an active receiver only for a group on 10 of them, I only send 10 copies at the ingress rather than 100 copies, which is quite a lot, right? So this uses type 6 SMET routes. Now, this requires state. Anything selective consumes state. So you can limit the amount of state consumed using a policy. You'd say, hey, I'm only going to do SMET for a subset of my multicast groups. Everything else, for my high volume groups, for my low volume groups, I'm just going to do inclusive replication. Now, when you're doing multi-homing, you need to add some more route types. And the reason for that is, when you have a multi-home system, your DF might be on the left, but your IGMP joins are going to the right. And your DF has no idea that this host is interested in receiving a multicast flow. So that somehow the DF has to be informed, right, that to permit this flow through. And that's where the join sync and the leave sync are important when you have multi-homing. Now, with the join, when you have multi-home systems, the join sync and leave sync ensure that the DF is always the one that sends the SMET route. And the join sync and leave sync ensures that the DF is aware that the SMET route needs to be advertised or withdrawn. Now, these are machinery that already lives under the covers of things like MC lag. The difference, so it's not like, hey, this looks complicated. Well, you're living with it today. It's just you don't see it. And the nice thing about EVPN is you actually see everything. And sometimes it's kind of like, wow, that's too complicated. Well, guess what? You're living with it today. If you use MC lag, you got all this stuff going on today. You just don't know about it, right? And so we're just kind of bringing it out with EVPN and making it standards. Okay, optimized inter-subnet multicast. It's a mouthful. I'm going to just say OISM. Basically, in typical multicast, right, at the gateway, you replicate again and again for every single subnet, right? With OISM, you only replicate once to an egress VTEP. The ingress VTEP only replicates one to an egress VTEP, regardless of the number of subnets at that VTEP. And this only works with edge routed bridging and introduces a concept of distributed DR and supplemental BDs. I'll talk a little bit more about it in a few minutes. Yeah, new procedures, no new route types. Okay, there's also this new capability called assisted replicator. And what the assisted replicator does is, ingress VTEPs, they send all their BUM to an assisted replicator, and the assisted replicator does the work of replicating. So the load, the replication load on the ingress goes away and gets transferred to the replicator. The replicator could be connected maybe with more capacity, right? Now you can have multiple replicators, so you can have a set of replicators. So your ingress VTEP can actually load balance across that set. If one of the replicators goes down, it just uses the remaining replicators. And yeah, I said this already. New procedures, there's a new PMSI tunnel flags, but otherwise there's no new route types. Now, all of this stuff that we spoke of, selective, OISM, and assisted replicator can actually be combined together, right, to create overlay replication that, depending on your topology, could be as efficient as underlay replication when you bring all of these things together. Okay, so, and finally, I'm going to go over, how do you do multicast in the existing overlay service models um, today. You can do it with an external multicast-only routers. So all of your unicast routing can happen in the overlay, and your multicast routing can happen with an external gateway. And in order to do this, you want to use incongruent multicast, namely with the use of MVPN. So your external gateways basically implement MVPN, and otherwise, if you do PIM-based, you must do congruent multicast. MVPN allows you to do incongruent multicast, so you can actually have different gateways for MVPN as well as versus multicast versus unicast. And you can do this for obviously pure bridged and both of your IRB-based overlays, CRB and ERB. Okay, so now that doesn't mean that the overlay itself isn't doing anything for multicast. It is actually doing ingress replication. You can optimize it with selective replication. You can further optimize it with assisted replication. And then you have IP multicast and CRB overlays. We can use a classical model in CRB. Basically, we give each CRB gateway a unique IP address in addition to its common IP address, its anycast IPs. And we do PIM signaling, and we do regular DR election at the CRB gateways, and we do regular multicast at the CRB gateways. So that's how you can do multicast in CRB. And then ERB, there's actually no implementations of this OISM yet. So, but this is basically the right model for doing optimized intersubnet with ERB. Today, the ERB, you don't get multicast at all, right? With ERB, it's just unicast. So the way it's, the ERB OISM introduces distributed DR and supplemental BD. Basically all the anycast, all the VRFs at the leaves basically become local DRs. You know, typically in a subnet you have, you know, one DR, right, for the whole subnet. Here, you know, the subnet spans across multiple leaves. Every one of those VRFs are DRs, right? But they're only allowed to